Hello, ladies and gentlemen, and welcome back to CS395. We have reached week 9. This is my final lecture with you all, and today we'll be talking about Z3 and Angr. Now, these mostly have, you probably don't know you've probably never heard of either of these two things, and they're mostly tools used for reverse engineering. But of course, reverse engineering is a pretty big part of binary exploitation. Hopefully, you guys have gotten comfortable with Ghidra by now, and these are tools that'll help you do your exploitation in the future in the big boy real world. And let's just take a look. Let's dive right in. So before we actually get started, you need to install these tools because this lecture is coming out after we have distributed the VM. So just run your sudo apt-get update to update your the package manager for Kali, and then do pip3 install z3 solver. Pip3 is the package manager for Python. So install we'll be using Python bindings for z3, and then pip3 install ipython3, which I will talk about later. And you guys get to see all the exciting stuff we'll do with these two things. And we also need to install Angr, but that's more complicated, so we'll talk about that later we'll burn that bridge when we come to it. So we have a problem, and that problem is that reverse engineering is hard on our tiny human brains. Sometimes you need to reverse engineer some very math-heavy code, and that can be very confusing. And you could try doing it on pen and paper, but no one really wants to do that, and that could take forever. And sometimes it's just not possible. So an example of this is have hashes, or generators like a CD key generator that proves that you have a valid license to own a game, or to play a game. And the list goes on. There's a lot of things where math-heavy operations occur. And reversing these takes time, like I just said. And even if you can run through them with GDB and try to see what happens, it's still just really hard to figure out. So the question of the day that we are trying to figure out and answer and find good solutions to is, given the output of this sequence of operations, and by sequence of operations I mean code that does math or does any mutation on an input, what must the input have been? So given an output and we have control of the input, what input gives us a certain output? That sounds really confusing when I try to say it out loud. I promise it is not that hard in practice. So the solution comes to us in the form of Z3 and Angr, and that is symbolic execution through static analysis. And this is a pretty in-depth topic. There's a lot of research that goes into something like this that goes way over my head. So if you'd like to read on that, please be my guest. There's a link to it there. New and powerful technology enables this technique. That's actually a complete lie. I should change that because it's not very new. Symbolic execution was thought up back in the 1970s, back when people were banging sticks together. It just wasn't really a possible technique until the hardware of today to test programs. We're going to be using the Z3 theorem prover with Python bindings to do our symbolic execution for the next couple minutes. And this uses computer magic and supermath to make reverse engineering easier. When we have control over a program's input, we want to reach a specific output, and we know what operations it does on our input. And we can do that by disassembling the code in Ghidra, which I will show you in a demo in just a second. But first we need to do some vocab. I keep using this term symbolic execution. Sam, what the heck are you talking about? What does that mean? Symbolic execution is a means of analyzing a program to determine what inputs cause what outputs. And this is all done without actually running the binary. This is all static analysis, which is analyzing a program without actually executing it, mostly through just code reading. But we can do it with some neat tricks with Z3, which I'll show you. So symbolic execution is when an interpreter follows the program, taking symbolic inputs rather than actual inputs from a program. So what does that mean? If we have some a C function that takes a number from the user and then adds 5 to it, and then it says, okay, if your number plus 5 is equal to 15, then we'll give you a shell or a password or whatever. we replace the user input with just an x. Like think back to 7th grade algebra when you're when you have an equation you're trying to solve for x. A symbolic input is basically we're just telling our computers that, hey, x isn't something that we're giving the program. X is, a variable that we want you guys to solve for. And then when the program goes to do the, okay, x plus 5, is it 15? Our computer or our Z3 will tell us, okay, then the input that you need is 10 to make 15. But that was that might have been a bad explanation. So let's just do a demonstration, and I'll explain what you guys are looking at here, and we'll run it in just a second. But basically, this is a program that takes 4 numbers from the command line, casts them to integers, and then does a bunch of math on them. You can see that it uses the first variable must be equal to the second variable times the fourth variable times 3, and then it does a bunch of math on all these, and then runs checks against them. They have to be these numbers, and if they are these numbers, then we win. But figuring out what those numbers would be very difficult, if not impossible, by hand. This is pretty small, so you probably could do it, but it would take a very long time, and you wouldn't be happy about your life while you were doing it. So this is a system of equations, just like from your 7th or 8th grade algebra class, which is a great job for the Z3 theorem prover. And we can do that in nice Python, the Python environment that we have come to love so much in this class. So I will show you guys how to do that right now in the VM. Okay, so here we are in the Demo 1 folder of our Week 9 section on the desktop. And the binary that we're going to be working on is called crackme from reverseme.c. So let's run it and see what we got. We just talked about what this did, but let's do it in practice just to make sure that I was understanding that right. So it tells us that I'll take 4 numbers less than 20 from you and apply my secret hashing to them. Give me the input that will produce 96, 1, 18, and 89. And then it said we gave it an invalid input because we didn't actually give it any numbers. So let's, I don't want to do any math or anything like that or any actual work. So let's just throw some numbers at it. Maybe the answer is 1111. No, call this root name. And we can see that we gave it 1111, and that gave us the output of 3, -1, 3, 2. But what we want is 96, 1, 18, 89. So okay, let's just try guessing again with some real numbers. Let's do 9, 12, not 29, 19, 2, and 4 or something. And that gave us some very wrong numbers, 1700 when we want 89. Okay, so we're doing something wrong. Let's go back to Ghidra and see what we got here. So we have all this math, and man, we could sit down and try to figure out like, what variable is something times another variable times 3. What does that give me? 4 or whatever the program wanted? No, we're not going to do that. What we are going to do is use Z3. We're going to do that in Python to solve this math for us, so we don't have to think that hard. So let's get started. Hopefully you ran the pip3 install Z3 solver command from the first slide already, so you can just from Z3 import all. And what we're going to do here is first we need to make our variables, the symbolic variables that the program will take as input and then do all the math on. So to do that, we can just say 1, our first variable, is an int, and this is a Z3 int, so this is a symbolic integer since we are solving for numbers here. So we can just name that whatever, call it A, and then we can say okay, yeah, so this next one will be 2, and we can just call that whatever, B. Really struggling with my Vim skills right now, it's embarrassing. 3, we'll just call that C, and this will be 4, and this can be D. Alright, so you guys get the gist. We have 4 integer symbolic variables now. Next, what we want is to actually, now that we have our variables, we want to take the math, steal this math from the binary, and then run it on our symbolic variables. But to do that, in Z3 first, we must make a solver. So solver object is the part of Z3 that will actually do this math. And actually, before we do that, let's we have to remember that the program said that our variables must be, the ones that we give it must be less than 20. And that will actually make this thing run faster. If it's doing a bunch of math to try to figure out what inputs will give us the output it desires, if we say that the inputs can only be less than 20, that really narrows its search down. So that's good. Thank you, program, for that nice charity work. So to do that, we can just do s.add, which is adding constraints to the solver. So we'll say 1 must be less than 20. And then we'll do it again for, we can say 2 is less than 20. And then we know that, oh man, 3 must be less than 20. And 4 is less than 20, whether you can believe it or not. All right, so now we have our constraints done. All that is left is to take a gander at the Ghidra math. And let's actually, we want to look at it, so I'll just do some resizing here. Okay, and now we want to take this math and put it into our Z3 script. So you can see that what we have here is we want to add that as another constraint as well, since these are constraints. And what do we have here? We have variable 2, so that's 2, times variable 4, and I am looking at this line right here, by the way. Variable 2 times variable 4 times 3 is equal to, 2 times 4 times 3, 2 times 4 times 3 is, and that's goes into variable 1, and that's expected to be hex 60. So we can just put that in our script, and then we can use the solver to say, okay, what's a number less than 20 that I can multiply with variable 2 and variable 4 and the number 3 to get hex 60. And basically we just rinse and repeat for the rest of the math in this binary. But I do not want to bore you guys to death, so I will cheat and just copy it because I've already done this before. And then to see our answers, all we have to do is print s.check, which will check to see if what we just told it to do is actually possible. And then print s.model, which will show us the results if this is possible math. So let's make this big again so we don't have to stare at the Ghidra. And if we did this correctly, running Python 3 on our demo.py will give us an error. Sick. All right, model is not available. Let's see what we got here. Unsat. So unsat means that the conditions we gave it, the constraints we gave it, are unsatisfiable. That's what unsat stands for. So we did something wrong here because this should definitely be satisfiable. So let me try to just take a quick look and see what we did wrong here. Okay, guys, I figured out what went wrong. I see now. So let's take a look at the Ghidra, because you can see that I said, these are out of order now. I said that this thing is equal to 2 times 4 times 3 is equal to 96. But if you go into Ghidra, var2 is actually the first number, and var4 is actually the third number. So that should actually be, where I say 2 and 4, it should actually be 1 and 3. So I have fallen victim. I was lazy. I didn't rename my Ghidra variables, and I paid the price for it. So let's fix that now so that we don't make that mistake again, even though we're almost done. Impatience, it gets you sometimes. You use cool tools like Z3 to try to cut out the work, and it bites you. It bites back sometimes. So 1 times 3 times 3 is our actual, the variables we want here, variables. So 1 times 3, I think it was? Yeah. Let's run that. That's the wrong script. That does work, but that's the example script. We're using demo1.py, which also works. See, now this time we get sat, so it's satisfied, and then it gives us back the variables it found that work. So they're out of order for some reason. But let's try running our crack me with these numbers. So A is 4, B is 2, C is 8, and D is 5. So if we run that, we get a congratulations, you win. We got 96, 1, 18, 89, just like it asked us for. So excellent. We did that almost first try. But now you can see the power of Z3. If this was a much larger binary, this would be more impressive. But for the sake of demonstration, this is a good one. You can see that there's math that we don't feel like understanding, and we don't have to. So that's awesome. Now let's go back to the slides, and I'll show you guys some other ways of doing this. All right, so that was pretty cool. You guys got to see the power of Z3 in action. And here's just another explanation of what we just did. I explained it pretty well when we were doing it, I think. But if you didn't get it, just check it over by reading this. But forget that, we're moving on now. So the problem is, I want to analyze a binary with absolutely merciless, unforgiving intensity. Forget this Z3 stuff, that was a lot of math, I had to think really hard about it. That's not good enough for me. I want the big kid tools, what do the researchers use? What's the bleeding edge tech here? Z3, it's for math, and I hate math. Give me something good, Sam, give me the good stuff. And I will give you the good stuff, young student. And the good stuff is Angr. It's the absolute holy grail of binary analysis. It's not as cool as Pwn tools, I'll say that right now. So lower your expectations a little bit. But what this thing can do is kind of incredible. So it uses Z3 under the hood to do symbolic execution like we just did, but makes it a little bit easier sometimes. It can actually do a lot. It can do a lot of what Pwn tools does, like a lot of reading and writing from ELF binaries, like scanning, that kind of stuff. It can make us ROP chains if we want it to. There's a huge API, and there's a lot that they can do on their website. And if you want to try to focus as hard as you can to understand the dark magic that goes into making something like this, here's a paper on a research paper on some of the stuff on how Angr was made. But that is far beyond the scope of my mortal brain that I can teach you guys. It has some dependencies that clash with Z3, so before we can use it, we have to install it in a separate virtual environment, and I will show you guys how to do that in a second. But mainly what we want to use Angr for is to emulate a binary as well as doing symbolic execution, which is a pretty powerful combo. I think I missed a slide. Yep. Okay. So yeah, like I just said, Angr lets us emulate a binary as well as symbolically executed, which is called concolic testing. We can give Angr the address of a win condition, or a win condition example of that being in this past binary that we just did. What we wanted to do was print, congratulations, you won. So we'd call that our win condition. We'd say, okay, Angr, go to the string, congratulations, you won. Run through this program. This is, we haven't shown you guys this, I think, yet, but Ghidra can do this. This is called the control flow graph. It's incredibly blurry. I couldn't get a better picture of it. Zoomed in more, but this is just a graph of all the potential states of a program. This is the graph of the binary we just did. So you can see it splits off. It does its thing. I've just, for the sake of demonstration, said that, hey, this is the win condition, and we'd say, okay, Angr, how do we get to here? What inputs do we need to supply this program to have it the code reach this point? And then Angr will say, okay, let me think really hard about it, and it'll analyze every branch. It'll say, okay, how do I get to here? How do I get to here? How do I get to these? And this is a pretty straightforward looking graph. Pretty much just goes straight down. But if you had like a really fancy big binary where the tree was huge and there's so many interconnections, you will thank your lucky stars that you had Angr and that Sam taught you Angr in CS395. Unlimited power. This is great. If you you can leverage your Angr abilities to solve, if you're a CTF guy after this, or a CTF woman after this, and you want to get into CTFing, then like 100 and 200 point reversing challenges are easy. You can absolutely, like, it feels like cheating once you learn how to use this stuff. Um, that's enough about me spouting about this. Let's actually talk about what it is and how we use it. So installing it is kind of a pain. I'll give it that. So I made us a script that'll install it for us, kind of. But I'll show you guys how to use that because it's really not. It's still not very straightforward. Z3 and Angr have conflicting dependencies. Even though Z3 is a part of Angr, they don't mix. So what we have to do is we have to create what's called a virtual environment for Angr, so that it can have its own set of dependencies for Python apart from our main environment. So that way it won't clash with Z3. And I'll show you guys that. And here's the command that we can't use yet because I haven't shown you guys how to install it. So let's hop into the VM, and I'll show you guys how to equip yourself with this amazing tool. Okay, so here we are back in the VM, back in our week 9 folder. And the first thing we have is, to install Angr, I've made a little script for you guys, angr install.sh. And actually, when you start out, when you download it off of Blackboard, it won't be green, it'll be gray like this. And that's because when you install something, a script off the internet, a binary off the internet, in Linux, it automatically turns off the execute permissions. That way, if you're a grandma, you don't accidentally run malware. But since I'm your esteemed teacher, you can trust me and run this on your machine. But give it permissions to run, you have to do change mod plus x angr install.sh, and this returns the execute permissions to that script. So now that that's done, what you want to do is run the source command on the script. Well, actually, first let's actually show you what's going on, because there is something that you can probably learn from just looking at the script. So what's actually going on here is it's just running update like I told you guys to do in the beginning. It's installing virtual env, installing a virtual environment wrapper, installing IPython, even though I already said to do that in the beginning of the slide, so you should already have that done. But just in case it's here, and then it's setting up virtual environment stuff, and then adding these two commands actually to your zshell rc file, or your zshell resource file. And the contents of this file are run every time you log in. So that way, instead of having to log on and then run the script every time you want to use a virtual environment, this will all be ready for you when you start. And then I just have some instructions that print. So then after that, you should be good to go. So with any luck, we'll only have to run this once, and then everything will just work. So source it, because we have to use the source command instead of just running it with a // because it changes environment variables and it's a whole thing. Look up the source command if you want to know more about that. But now looks like we're installing our stuff. All right, cool. So that's all installed. And now we can make a new virtual environment using make virtual env. It looks like everything worked. And then we can install Angr. So let's see if this actually turns green. It does. Okay, sweet. This is not my first recording. I'm happy to see this work. Make virtual env. We'll call it Angr because that's the only thing we really want in this environment. Cool. That seems to have worked. And now you can see we have Angr in parentheses over here. That means we are now in our Angr virtual environment. So our Python install does not have, well, let's just check it out. We go into Python 3, and if we try to import, what's it called? Z3. Yep, module not found. So we have different basically a clean install of Python. There's no modules loaded in. So that way there's no way to clash dependencies for when we install Angr, which we're going to do right now. Now that we are inside our virtual environment, we can pip3 install, I think it's just called Angr. Yep, awesome. It's working like a charm. So we'll just wait for this to download, and then you guys can see the amazing features of Angr and how we can use it to solve the crap out of some binaries. And there's a lot of dependencies that go into it, so this might take a good minute here. Yeah, okay, I'll be nice. I'll end the recording. Oh, never mind. Okay, yeah, so we just finished it. And that's installed. So let's double check that that just worked by going back into Python and trying import Angr. And do we get an error? No, okay, it worked. Excellent. So we're in the Angr virtual environment. If you want to leave it and go back to the to your main environment, you can just type deactivate, and then you're back in. So now we don't. If we go back into Python 3, try to import Angr, if we actually spell it right, it doesn't work because it is not installed here. So to get back into it, you can do the work on command, and that'll list off all of your virtual environments. And we want to work on Angr, so we're back here, and we have access to Angr again. Excellent. Now let's get back to the slides, because I don't think we're at the demonstration yet. Okay, we're back. We have successfully installed Angr in our virtual environment, and hopefully that is all working. If not, drop some questions in the piazza or show up to the office hours, and we'll try to help you figure that out if you can't do it yourself with some good old-fashioned Googling. So, Angr demo. I've talked the talk, but can I walk the walk? Can I show you guys that Angr is actually a cool tool? To show you guys that since it has Z3 in it, it can do anything that Z3 can do pretty much. So we'll solve the binary that we just did earlier, but in the Angr way. So yeah, let's just get straight to that. Okay, so let's finally dive into our Angr script and see what all the fuss is about that I've been making. So step 1 is just import Angr. Step 2 is import IPython, which I haven't actually told you guys much about, but it's easier if I just show you than tell you, and there'll be a slide on that later. But now the main, a big difference from the Z3 script and now is we're going to import Clarify. And what Clarify is it is just a Python wrapper for Z3. So when you see Clarify, this is just Z3, but it's the version of Z3 that Angr uses. But under the hood, it is the same stuff. So from Clarify, import all. And I'll show you guys how that's different as well. So now the first step is to make a project for Angr. Just like we have to load in our binaries and pwn tools, we have to load in our binaries in Angr for it to scan. So to do that, we just say specify the binary here is called crackme in this directory. And then also it's a good form in this class, or just kind of in general, is to turn off the auto load libs option. And what this does is instead of loading loading libc, what Angr wants to do when it's analyzing a binary is to load libc into memory, or anything that this is actually anything that the binary is linked to. It wants to load that into memory so that it's faster and that it can hook functions and do a lot of fancy stuff that we won't be using and that you won't use 90% of the time in the real world anyway. And it can get in the way of some of the stuff that we want to do here. So we'll be turning that off always in this class. So yeah, we have our project set up. And now, just like our Z3 script, we want to make our symbolic variables. Only we're using Clarify now, not Z3. So making these symbolic variables is a little bit different. Before we could just use that nice integer constructor, that capital I int constructor for making our variables, but now we're using BVS, which stands for bit vector symbol. And I did mention in the last script that another name for a symbolic variable is a bit vector symbol, which is all we're using here. It's just a different name. And it's generic, so it doesn't have the integer type that the Z3 version had, which is kind of a bummer, but it's just what you got to deal with Angr on this challenge, unfortunately. I will tell you guys about these 16s later, because it won't make much sense right now. So we'll just run this, and this is taking forever, so let's speed that up. Vim should be your best friend in this major, Mason. Okay, so yeah, we have our symbols. Those are done. Symbolic variables established, bit vectors. Now what we want to do is tell Angr to create a state, and specifically an entry state, which is basically just a snapshot of what our program looks like when we first run it. And to do that, since for this challenge we need to pass numbers through the command line, it needs to take command line arguments, so we need to specify that argc is equal to 5 because we're passing 4 variables, and the name of the binary is always passed as the first variable, so that's 5 in total. And then we need to say that args is equal to a list of what we're inputting through the command line, and the first is crack me. And now the second is our, the next 4 variables are of course just our symbolic variables. Now I can tell you guys the reason why these are 16. So this means that these symbolic variables are 16 bytes wide. And that is because when we're passing our numbers through, oh, I did this wrong. When we're passing our numbers through the command line, they're actually being interpreted as strings and not integers. And that's why if you go look back at the Ghidra, you can see that our inputs through the command line are getting casted to integers through the a to I command, because they come in as strings and they have to be turned into integers. So since we know that our that it wants our, man, I got confused there. Since we know that the program wants our input to be less than 20, 20, that's 2 characters. 2 characters is 16 bytes. So our symbolic variables are 16 bytes long, representing 2 characters for Angr to solve for each of these symbolic variables. All right, hopefully that makes some sense. So the next thing we want to do is make a simulation manager, or a simager, whatever, as it's shortened to. And we do that by using the factory field of our project, which basically just makes us these nice things that we're using, simulation manager, and we pass that our entry state. Simulation manager just takes the state, which is basically just a snapshot of memory, and allows us to simulate what running the program actually looks like with these states. And this is what lets us step through a program and find and look through all the paths and do its angry magic, which I will demonstrate right now with this. This is the most magic function in the whole Angr library, and that is simulationmanager.explore. Now we have to actually tell it something to explore. So let's look at our Ghidra again, and we need to track down our win condition, which is very easy here, because winning this binary is as simple as having it print, congratulations, you win, and finding the 4 numbers that it's asking for to give these outputs. So we want Angr to execute all the way down to where it manages to get congratulations, you win to print, and then we want Angr to tell us how it got there, what steps it took, what inputs it used to reach this branch of code. And I promised I would show you guys the control, the function graph, which is located right up here in this symbol. So we're going to say, okay, Angr, how did you avoid this branch and then go into here, and what inputs did you use to make it all the way down to congratulations? How did you pass all of these conditions? And it'll tell us, which is awesome. So I didn't actually get what I came for. What we need is the address of the congratulations string, which we can see here is at that address, and we can just copy it and then go back here and say explore and set the find key variable to our address. And now this will say, okay, Angr, explore, do your thing, simulate this binary and find out what it takes to get to this address. And once it has done that, we can do ipython.embed. And that's exciting too. So I can't wait to show you guys that. So what we're going to do is just run our script here. demo1.py. Okay, it doesn't feel like auto-completing, I guess. Hopefully this works. No module named IPython. Did I not install IPython? Right, we are in the Angr virtual environment. So, and I didn't install IPython here. So, yeah, we need to do that again. My bad. All right, that's done. We'll just run demo1.py again, hopefully with better results this time. And this might take a little while because Angr has to do some serious math, some serious thinking. All right, and we're here. All right, so what you're looking at is a Python interpreter. And you might wonder why this is useful, but this is actually this is an interpreter within the context of the script we just ran, which means we can access the variables of our script. So if you remember, we had a simulation manager named Simager, and we can check that out, and we can see it has it's working. It found it ran four searches down the tree of this thing. So you know, it looked here. It's like, okay, that's one search, and that's two, that's three, that's four, and then the fifth one managed to find our Explorer address. So it reached our condition. So what we want to do to access that that state, because that is a state that it found. So we want to do simulation manager dot found. It's a list. So we just want to access the first element there. And we'll see that, yes, there's a sim state at the address that we asked it to find, which is awesome. And so now we want to see, you know, if we wanted to, we could look at the other active states, but we don't care. So now we want to do found 0, and then just like Z3, Angr has a solver. And then we can use that to evaluate our symbolic variables. So if we do that, you can see that it gives us this random looking number here. And actually, that's not what I want that to look like. So let's remember, we're solving for a string here, not a number. So it just gave us a number, but we want that to actually cast to bytes, I believe. And that'll say b plus 4. Okay, so yeah, so this converts this random number to the string, basically, that it actually gave it. You can see that it gave plus 4 to the program as the first argument, and that's kind of weird. But I promise you, this is working as intended. So let's quit out of that now that we know that it worked, and let's go back into our script here. So we know that the Explorer works and it found the correct address. So now what we can do is, let's finish our script, because we don't want to do everything in IPython. IPython, when you embed that, you're mostly doing it to test your script, see if everything is working the way you thought it would. And it's great. So it's good for testing stuff. And it's a good environment to work in for things like this. So anyway, we're making a solver variable just so we don't have to do a bunch of typing. So we take our found state and create a solver for it, and then we just want to write a nice little series of eval statements that'll evaluate all of our symbolic variables and turn them into bytes so that we can easily read them and then use them in the program. So let's copy these. Okay, that looks good. And replace that. That should be 4. Okay, cool. So now if we comment out IPython, if we run our script again, it will tell us, hopefully, all of our symbolic variables that it found on its way to our Explorer address. And I know that this is definitely more complicated than the way we did Z3. This, in all fairness, this binary is definitely more suited. These the small, simple math is more suited to a Z3 solution than an Angr solution. But I'll show you a cooler Angr solution later. But here we have our results. We have +4, 7xe8, which is weird, 8 caret, and 0, 5. And that looks crazy, but actually if we run crackme with these inputs, 7, I'm going to forget the xe part, because that's, yeah, no, forget it. We use the 8 caret here and 0, 5, although actually the terminal doesn't like it when you use those redirect symbols on it, so we have to put those in quotes. But then if we run it, we can actually see we won. We got a congratulations. Sam, how the heck did that happen? These special characters get stripped away in the A2I call from Ghidra. So when it's converting the string to the integer, it gets rid of those weird characters, and it just takes the numbers here, which is good. So cool. We did this the Angr way. As complicated as it sounded, Angr is a very complicated program. But in better cases, unlike this one, we can actually do a lot of really powerful stuff with it. And I will show you that in the next demo, because we have another Angr demo, baby. Okay, we're back. Now I just have a couple slides. Obviously, that was not short. That took a while to explain everything that Angr does. So that's what these next few slides are, even though I talked about most of it. This is a good review if you didn't get anything, or if you missed something. So let's just step through here. There's not a lot left that I think we need to talk about, other than the fact that I have linked the API to some of these objects here in these slides. So you should definitely take a look at a sim state and see what those are if you want to understand really more how Angr works and why we do the things we do here, the explore function, and what a simulation manager actually is, and then how the solver works as well. So we did that. Now let's talk briefly about IPython before we get into the next demo. It is just a souped up Python interpreter, and what I mean by that is maybe you're used to working in Python like this. You know, this is what your Python interpreter looks like most of the time. It's boring, it's drab, it doesn't do a whole lot. But if you use Python 3, or not Python 3, IPython 3, if you encounter problems being solved by Python inside the, okay, yeah, whatever. Now you can see we have a much prettier interpreter. So it's not just prettier, it also has useful features that you want, like tab completion. So if I want to do like sim something, you can see I have a bunch of different things to choose from, and I can scroll through and use those, which is cool. But then say that you're working in something new, something you've never used before, like Angr. And I have a sim state selected here, but I don't know what the heck a sim state is. If you put a question mark next to it, it doesn't have this one. I guess that was a bad example. But I think if we do this, yeah. It basically just brings up a man page for it if you add a question mark next to a Python object that you don't know. And it'll tell us a bunch of stuff about what a sim state is in Angr. And that's cool. That saves you time. Now you don't have to Google it. You can just use it in IPython. So that's just a nice tool for you guys to use. And I think it's mostly useful for being able to embed inside of your scripts. That's very useful for you know, live demos and testing. But it's useful for a lot of things. So just thought I should have an honorable mentions slide for that. And you can flex on your friends that you have a cooler Python interpreter than them, because that's what people brag about in the CS major, I think. Anyway, Angr demo 2. Let's get into this. We have a binary here that might look similar to some of you, because all it does is it's asking for 3 passwords, and it asks for passwords and then compares our input to it. And for this challenge, we're gonna pretend like the passwords aren't just hard coded right in front of us, and that we can just see them all. But this might ring some bells for you guys. This might remind you of the binary bomb from 367 if you've taken that class. And I'm gonna let you guys in on a dirty little secret, is that if you use Angr on the binary bomb, man, you could do that thing, hundreds of times faster than the way you're supposed to do it. Of course, if you've already taken the class and you still have your bomb lying around, you can try that. If you haven't taken the class, don't use Angr on it, because that is cheating, according to the establishment. Anyway, let's get straight into the demo, because this is dragged on long enough. Okay, so we're now in our demo 2 folder, and we're about to do a cooler Angr problem, one that crappy Z3 couldn't hope to achieve in this amount of time. So come on, get out of here. This is the wrong one. All right, yeah, cool. So we're looking at a password checking binary right now. And that's, not just easy math. This is like a whole thing. It's asking for passwords. I truly have no idea. And it won't let us in. That's horrible. But, it looks like it's doing the password checking in the binary, and we're going to pretend that instead of just string comparing just to a string that's just hard-coded in, it's doing some sort of string manipulation inside of this thing, or maybe it's calling back to not calling back to a server. I guess that wouldn't work. But if it's doing some advanced hashing or anything like that, or perhaps this is the check for this password is hidden someplace else in the binary or in an external library, you could hit that thing with Angr. And I will show you that we can do this. We can solve this whole thing in basically 3 lines of Python without even trying. So these are bold claims. Allow me to back them up. We're going to start with import Angr, and we'll use IPython again. And step 1, just like before, is making a project. I'm just going to call it crack me again. And we'll do the classic load options, turn those off. And this isn't very exciting, but the power that you wield with this with Angr is quite great, as you will soon see. So make a state. We'll use another entry state here. But this time, since we're not passing any arguments into the command line, we don't care about argc, we don't care about argv, we don't even need to make any variables, any bit vectors this time. Because we just want to solve for local variables, or local variables for input that it would take dynamically at runtime, and stuff that's already baked into the program. Anyway, so we have our state. Now we want our sim manager, and then we'll just call that sim manager again, hand it our state, and now we just want to do our explorer. And now we need to find our win condition. So we have a great job string right here. That seems like a good place to do it, because you can see this is printed after all 3 string checks are good to go. So we'll just take that address and go back to our script, put that in, and then we'll embed IPython to see if that actually works. And that'll run. Name sim is not defined. Oops. Sim manager, my bad. Okay, so now it's spitting a bunch of stuff out, but this is okay. This is just Angr telling you what it's doing. It's saying that it's trying to, string compare values that don't exist. It's trying to, so now it's saying, okay, it's comparing something that's supposed to be an input to a password, and now it's figuring out, okay, I will figure out what this input is supposed to be myself, and it's just telling us that's what it's doing. So let's check on our simulation manager. We have 1 active, 2 that dead-ended, which means they didn't find anything and the program exited, so they failed twice essentially, and 1 found where we're trying to go, which is awesome. So let's check that out. Check out the first one and do it correctly maybe. So found, yep, that's at the correct address, I believe. And then we want to see what the what Angr determined the standard input would look like for this to reach this state. So we can just do that, and it won't work because that is not how that works. We have to do POSIX.standardin, sorry, because that's just another another wrapper for interacting with the operating system. Because Angr does work for multiple arches, which is amazing. So there's no reason not to use it, no matter what system you're on. So it'll tell us that, but that's not useful. So we want to use the, I always forget what this is called, this command here. Luckily, we're in IPython, which has tab completion. So the command is called concretize, which is just weird, but it will print out, the list of things that it had to, inputs that it had to use to get to where we are from standard input. And you can see that what we have here is 3 passwords. So let's try those. We have password, secret, and CS395 with some more random characters here that we can safely ignore. So let's try that. Actually, that's not how this works. Just run the crack me, try password. Oh, that seems to have worked. Let's try secret. Wow, okay, and CS395. And yeah, we're Angr masters, baby. All right. See, this is what I'm talking about, guys. This we can cut this down. This is so quick, so easy, super powerful. We could cut this down to like 2 lines if we really wanted to, but this is not a short programming class. This is for epic hackers like ourselves. So that, yeah, concludes this demo. Let's get back to the main slides and finish up my, my last lecture. All right, so we got our Angr solution that we just did together. Basically, there's not much to talk about here, actually. This is pretty much what we just did. I will say that while Angr is very strong and awesome, it is also very finicky. It's a very complex program, so a lot can go wrong. And that's why it's nice to have IPython to debug, try to figure out where things are stopping and why they're hold up. But for programs like the demo we just did, it is amazing. And I highly recommend that if you guys go into exploit dev or reverse engineering careers, you try to figure out how to use this, because I promise you that this will look good on a resume. Or if you say, oh yeah, I know how to use Angr and Z3 in a interview, you will look like a smart person. But yeah, that's all I have to say about that. And man, that's my my last slide. I guess we're done here. You guys have finished all your homework, so you're now just focused on the final project for the remainder of the semester. I hope you guys enjoyed the class and me and Nihal's lectures that we worked very hard on, and that you learned something that you found interesting. Hopefully you're now you want to go into an exploit dev, reverse engineering kind of career path, and if you are, I can guarantee you guys what you have learned from this class so far is not just a bunch of lame stuff or just just baby hacking. These are actual interview questions. If you sit down at like Raytheon or Lockheed or or like FireEye or a big defense company for a position in cybersecurity where you would do this kind of thing, they will ask you about buffer overflows. They will ask you about string formatting vulnerabilities. They'll ask you about ASLR. And those are all the basics that we have taught you guys, which is awesome. And now you even know, Angr and Z3, which are like, more advanced topics that you can really flex on people with. And Nihal's next week is going to teach you guys some binary patching and some awesome stuff like that. So I can say with confidence that you guys are prepared, and definitely have a leg up now. So I guess all I can say is good luck. Thank you so much for sticking with us this semester. I hope you have enjoyed it as much as I have. If you have any questions on the final, of course, Piazza, email, office hours. Me and Nihal are there for you guys all the way through. And have a good rest of your day and have a good rest of your semester.